Ruediger Urbanke from EPFL. So Professor Urbanke is one of the leading experts in coding theory. He won many, many awards, including the Hamming Award, Richard Hamming Award last year. And over the last few years, Ruediger has diversified and went more and more into entertainment. And if you want to know more, just look it up on YouTube. You'll find an 18-second clip that has been downloaded more than all of his other talks combined. Okay. This I would like to leave you the floor.
So I would like to start thanking Claude for inviting me. It's always a pleasure to be in Paris. It's a particular pleasure to be in these halls, these famous halls with all this history here. It's an even greater pleasure to have so many of my heroes in here, Claude, and I see Bob Gallagher, and you see all these, Janos, and whatever. I don't want to now insult anyone by not mentioning. I would have to go through the whole audience, and it's an even more greater pleasure to do it here, for the Shannon Centennial. So what I would like to do is to do the following. It's 68 years since Claude Shannon introduced the problem of coding, and that's indeed a very happy number. It's now also his 100th birthday, and what I would like to tell you is that this problem of coding is an absolutely beautiful and fascinating problem because if you look for the 68-year history, there have been many, many ideas, some coming from information theory, some coming from algebra, some coming from statistical physics, probability, all kinds of different areas that have influenced how we actually do coding these days. But all of them have nevertheless the same aim of just an efficient information transmission. So what I would like to do is to go over some of these key ideas. I don't think I have a single formula in my things, but I have lots and lots of pictures. And so hopefully I can convey a little bit some of the excitement and joy and the variety of ideas that have come into play. Good. So you probably have over the last 2 days seen, of course, Shannon's paper and where he introduced the notion of capacity. So the notion that you give me some physical medium, wireless, some cable, there's some maximum amount of information that you can transmit reliably over this. And that's what's called the capacity. And this will be what our aim is, trying to get in an efficient manner as close as possible to this capacity. And so he gave us, of course, more. He gave us a whole setup. He said that, okay, once you have a certain channel, a certain physical medium, you mathematically describe the essence of what this medium does, what kind of noise it introduces, how it acts on the input. And then he gave us, so for example, in case you want to think of something this very concrete, think of what's called a binary symmetric channel. It's a channel in which simply bits come in, bits come out, and for every bit there's like some little malicious genie in there which decides with some particular probability to flip that bit, and these flips are done independently. And he gave us also a setup saying, okay, if you want to transmit information reliably over such a channel, then do it by using what's called a code. So in our case, we'll always think of binary code. The elements of this code are just code words. These are n tuples here. In this case, it's very small. These are 3, what you should think about in practice. The length of these code words are from hundreds to literally hundreds of thousands, so very, very long. And so you have these code words. And how many are in there? Well, you need a lot of them in there. If you have length n, you need something that's exponential in here. So if you have a code of, let's say, length 100,000, and you want to transmit about half a bit per channel use, you'll have actually 2 to the 50,000 code words in the code. So these are pretty big objects in here. And that's what we want to do. We want to find a code that allows us to choose one of these. The choice will be the information that we want to carry. There will be some perturbance. We'll receive it at the decoder, and we want with high probability be able to detect or decide what was it that actually was transmitted. So what were some of the many ideas that came in here? So historically, the first one was the notion of minimum distance and packings and algebra. And so I'm happy to report that one of the first guy was a Swiss guy, okay, Gaulet, but then there are many other ones all around, so early 50s or until the 60s. And these are some of the famous codes that were introduced, and we'll come back a little bit later to them. And in all of them, the idea was that if you're thinking now as these sequences, this binary sequence of length n, and of course I can only draw in 3 dimensions, as the points in a cube, which are now called the Hamming cube, then your problem will be now finding a code is choosing some of these points in this cube. And you want to choose many points, and in particular, you want to choose the points that they are well separated. And so this led naturally to the question, how many points in n dimensions can I fit into such a cube such that any 2 points are separated by at least a distance d? And that turned out to be actually a very, very difficult problem. So asymptotically, this tells you that for, given that you want a certain distance, what's the rate? So the exponent of the number of points that you can fit in here. And we only have upper and lower bounds. So there's a problem that's by far not what's the best kind of packings far not solved. And so what was the idea? Why do we want this? Well, it is kind of natural. Because if I have a point and I'm sending it, and even if I have now a small error in here, so some of the bits will be perturbed, well, if I have a very large separation, if this point is not too far away from where it originally started, then I should be able to go back. In particular, if I don't make errors larger than half this distance that's guaranteed, then I should be able to go back. And particularly if these kind of codes come from some very nice description, in particular, these were algebraic ideas, polynomials, finite fields, and they had some very nice description, then there should also be an efficient algorithm to do this. And so this was indeed the idea of algebraic codes, these classical codes with what's called bounded distance decoding. And this was used, and is still used, early space exploration. Maybe some of you still remember what that thing is, okay? And this we still certainly have all in our computers. Okay, so basic idea was you define a code, you define this set of points you want by some algebraic structure, and you use this algebraic structure, first of all, to find good packings, but then also in the decoding process to do this efficiently. And but it is a quite difficult problem, and still until to this day, we don't know what actually the best kind of packings are. Now, it turns out that very difficult is the binary case. If you go to a very large alphabet, it's much easier. Unfortunately, really, what we really need typically is binary or very low alphabet things. So that's the hardest one. OK, now, the next idea that came along not so much later on was that when we're actually sending information, we are not sending this abstract 0 and 1. We have to, there's a physical process, we have to transmit this. And this physical process simply means that we're sending a signal, and we can think of the signal as a point in, let's say, Euclidean space. So for example, we might send, instead of a 0, 1, we send the value, real physical value of 0 and 1. So we embed that in an actual space. And so these are just various ways of how we can either take single bits or combination of bits, embed them into a space. And so now we have a kind of similar problem. So now we can still think of points in space, but we're no longer thinking of this Hamming cube. We're thinking really of embedded in Euclidean space. These are points in space. And so now, again, we're trying to pick points in space. These are the code words. But now we can use geometry, right? So now we have really, instead of this abstract problem that we had before, and we really have one of the standard, packing problems. And that, of course, has been studied, going back to, Kepler and probably even much earlier, right? So we can use the geometry, and the geometry can make things easier for us. And indeed, these two concepts are not completely separate. It turns out that one way to find points in Euclidean space is to take one of these Hamming cubes that I showed you beforehand, let's say one of these cubes here, okay? And just think of now, instead of the Hamming cube as really a cube, a physical cube with side length 1, and then taking the points that you have in this cube, the ones that you have chosen from an algebraic code, and then just simply take the cubes and translate it and fill the whole space with these cubes. If you do that, you actually come up with something which is called a lattice. A lattice is just a set of points in some, let's say, Euclidean space, which is the integer linear combination of some base vectors. And these would be the points, the code words that you actually had. So there's a way to take an algebraic classic code and embed it into, into Euclidean space and get now a packing in Euclidean space. And typically, since we also have something which is called an energy constraint, we cannot just send any point, but the point, the further away is from the origin, that more energy we have to spend. We typically take a lattice and then have to, cut off just some, the points that are somehow inside, and that's what we would actually send. But it turns out, that that's one way. Now, what are the best lattices? What are the best packings? Again, that's actually a very, very difficult problem. And again, in general, we don't know what the best packings are. But here are some of the nice, these are just geometric, low-dimensional representations of some of the famous lattices that people have defined and how they're related to some of these classical codes. But it turns out that, again, we're trying perhaps to solve a very difficult problem, and perhaps we don't actually need to solve such a difficult problem. So one of the ideas that came in and is due to Gottfried Urbanke was that let's assume, just to keep it simple, we're having just points in this two-dimensional thing that we want to send. Now, these points might be too close. So if I'm sending, let's say, this point, then a small perturbation, just think of a small deviation, some Gaussian noise, might bring it too close to another point, and we might no longer be able to know if it was this point or that point. But let's assume we split this point. This is called set partitioning. And so, we have just one bit that decides whether we take this subset or this subset, the union of those being the original. Perhaps we do it a few times. If we're looking down here now, let's assume I know this bit and this bit and this bit, then these points are much, much further away. Okay, so perhaps now these points down there are already so far away that it is very unlikely with the noise that I'm seeing that I'm ever going to make a confusion. So his idea was that if I'm starting with a set, and in general these things are of course much more complicated, if I perhaps just take a few bits to separate them out, then what I'm ending up with, okay, so think of here of the leaves, might already be doing very well. And so how can you use that? Well, you don't need to use any kind of coding down here. You can just make decisions. These are, you will hardly ever make a mistake here. So you only maybe on some of the bits actually have to use coding. And that means you have to have much less processing that you actually need to do. And it also means that if on these kind of things, maybe the kind of rate that you get for the particular code is not very good, well, you're only losing some rate for this particular bit, but not for the other one. So it means using the geometry and using this trick, much less effort to be done, and you're not trying to solve this very, very complicated lattice problem or this very complicated problem of packing. So again, these were used in many things, modems. I'm sure some of you still remember these modems, and these are exactly lattices, and ideas were exactly in these kind of products. So idea here, use lattices, use the geometry, and if you use the geometry, you can actually simplify your life. And one thing I have not talked about at all, which is something very nice, rather than using algebra now, you can use number theory to come up with some very beautiful lattices which have nice properties for things that's called fading channels, something that I haven't told at all. These are channels where, let's say, in some dimensions, you might simply collapse at all. So, the whole observation might be gone. And so now you have to think about, instead of getting, let's say, points in 3 dimensions, it will be 100,000 dimensions, but let's say 3 dimensions, you just get, let's say, something 2-dimensional. So you're getting projections. And so clearly you can see that this could be a problem in general. But by using number theory, you can define some very good lattices which can deal with such cases. Okay, so now it's a particular pleasure to have now the 2 people in here that are responsible for the next one here. So far, we've talked about packings, minimum distances, trying to pack as many balls or points in a space. Now, let's completely forget about this, okay? So I still remember that in '93, I was a student somewhere, suddenly there was all this excitement about new codes, much better than anything else, much lower complexity. And these were, of course, Claude Berroux and Glavier's turbo codes. And, they clearly have revolutionized the way we're doing things. And so what then happened is when people started to look at it and they started actually believing that these things existed and were real, is that people from physics and people from computer science and people from AE, somehow all with different ideas converged. And what was discovered that in the 60s, Bob Gallagher in his thesis had introduced what was called low-density parity check codes. And if you, once you put this all in the right framework, it turns out that these are all the same kind of concept. So there's some three fundamental ideas that, that both of them had introduced. Bob's codes at that time would have absolutely revolutionized the way communication is done, but simply, I guess, technology wasn't ripe to implement them, and so people had completely forgotten it. So what were these revolutionizing ideas? I apologize to Claude, I'm using LDPC codes to demonstrate just because I had already a drawing, okay? So these are just Bob Gallagher's low-density Parity codes. These are now 20 bits, again, think about thousands of bits. And so now what we do is, we have these bits. If we just send them, we don't know if when a bit gets messed up, how to reconstruct. So we need to put some what's called redundancy in there. We need to put some constraints in there so that we can use these constraints to recover. And so the way we will do it is that we'll have these local checks. The local check simply is an XOR constraint saying that whatever this check is connected to, these bits where this is connected to, these have to add up to 0 modulo 2. So these are local checks. And so any linear code can be written in this kind of way. So if I have here 20 degrees of freedom, maybe I'm taking 10 checks here. This takes away 10 degrees of freedom. Such a code, so the set of all the words that fulfill all this constraint would have what is called a rate-a-half code, because I have still 10 degrees of left out of all the 20. Now you have to think again of 10,000 or 100,000 such things in a real scenario. Now what's special about it, and which is one of the fundamental ideas, is that what I want is that these constraints are very local. They only have maybe 6 neighbors, and maybe here they have maybe only just 3 neighbors, and that's crucial. And why is this crucial? Because if I take a code like this, then what is it that I really should do? I send such a code, right? So one of these things that actually fulfills the constraint. Some of the bits will get perturbed, okay, in a particular way. And now I want to recover. And what's the optimum recovery strategy? Well, we've heard already map rule before. And so what we should do is we should maximize the posterior. So we have given the observation y, and we want to figure out what was the ith bit that was actually sent. So we should compute this posterior probability and then decide on this bit being depending on which of the two is larger, right? The 0 given y or the 1 given y. And it turns out that if this code is defined by these local constraints which have very low degree, then if you write this down, you can write this down in a form that is highly factorized. So each of these factors, this probability, only depends on very few of these parameters in here. And so this is what's called the factor graph these days, which is essentially exactly what we had before, but now we're also seeing these conditional probabilities of given, we have the observation here, so these are the likelihoods that we see this comes from the channel. And it turns out that if we have this highly factorized, and then this is a very sparse graph, and if it's a very sparse graph, then it turns out that some local greedy algorithm, which is called message passing, which Bob Gallagher had already used in his thesis, that such an algorithm performs actually very well. Okay, so it doesn't do the map, in general, the map problem exactly. It will not get you exactly this thing, but it will work actually very well. And what is message passing? Well, if you haven't seen it for the binary ratio channel, it's particularly easy. All you're doing is you're trying to greedily figure out by sending messages back and forth if you can't figure out one of the bits. So the basic idea is that if you have, for example, this constraint, right, which says that these 2 bits XOR have to sum up to 0, well, if, for example, you know this thing, but you don't know this one, then you can simply, via this constraint, fill it in. And so you just go back and forth by sending locally from all the bits what their knowledge is currently. You're trying to see if you can resolve one of the bits, and you're going back. And you're simply going back and forth. And that algorithm is called message passing. This is for the very simple case for the binary ratio channel. In general, you're sending probabilities back and forth. But it's a very low complexity algorithm that works very well if this graph is sparse. Now, what is nice is that, at least for some simple things like the binary ratio channel, this algorithm you can actually very nicely analyze. And at least for the binary ratio channel, the analysis, once it's all said and done, actually turns out to be something very simple. So this is for such a low-density parity check code. And for turbo codes, you would have something very similar. So let's assume this is the erasure probability of the channel. And you're thinking of a code that's really, really large. Okay, so you let it go to infinity. And so now you're doing the following. You're just running. So you're sending a code word over this thing. You're getting a certain fraction of erasures. You're receiving them, you're running this message passing algorithm, And so what can happen is that either you resolve all the erasures that you have here, or perhaps you get stuck. And so how does this in the asymptote behave? You can compute this. If you're plotting here the probability of erasures that's left at the end, and this is the original channel parameter at the start, then it can show that there's a very nice curve that has a very, very simple description. So this is the erasure probability end, this is the erasure probability in the beginning, and these are the 2 degrees that you have in the graph. Okay, so a very, very simple relationship exactly describes this curve. So asymptotically, you get a very, very simple way to assess whether the code works or not. How do I see if a code works? Well, this is erasure probability 0 here, so everything up to here, up to the 0.43% of erasures, you see that at the end when you're done, where you get stuck, you have 0 erasures left, okay? But as soon as you're above, there's a threshold, things will go up, okay? And so now for a particular channel, let's assume this code has rate 0.5, then the capacity for the erasure channel would be 0.5, but I would like to have that this jump happens exactly at 0.5, okay? This is for a particular code, so can we actually do that? Well, because we have some degrees of freedom, how are we choosing these degrees? Then we can try to figure out how to choose the degrees that this dynamical process will succeed with high probability. And indeed, this was done in this other very beautiful paper, you know, Luby, Mitzenmacher, Chocolai, Daniel Spielman. And so they actually found out how to choose these degrees such that indeed you can achieve capacity over the erasure channel with very, very low complexity. And for general channels, it's a little bit more difficult. So this is, you know, these are now, this is the best you can possibly achieve. And this is for the Gaussian channel. And so this is for specific lengths now. You have to do some numerics. But you can see that you can get extremely close and, you know, indeed essentially get as good as achieve capacity with these kind of schemes. OK, so again, where are these used? These are used everywhere. OK, there's almost nothing that you ever touch and communicate or store where you're not using either turbo codes and LDPC codes. And this will also, you know, stay true for the next generation, you know, wireless systems and all other kinds of systems there are. This is what you're really using. This, you know, you can thank these 2 gentlemen in the audience for making your life much less error prone. OK, good. So basic idea. Forget about minimum distance, okay? Whoever said that we should look at minimum distance, okay? You get to minimum distance, extremely difficult problem, and it's neither necessary nor sufficient. You need some minimum distance, but you don't need this optimum thing. And then use this message passing, and if you choose the graph right, works great, right? And then you have to use some irregularity, and it's also very natural to bring in what's called soft information, so meaning not just whether it's flipped or not, but it could be the channel is slightly worse or not. So this works great. Low complexity is a fantastic scheme. Good. Now, so we have seen already kind of 3 different ideas that came here. And so you might say, are we done yet? OK, is that it? No. OK, it actually turns out there's still some nice other ideas how you can also achieve capacity. And so the next really nice idea came along in 2008 by Erdal Arikan, who showed us how to also achieve capacity. And what's so nice about this is the following. Whenever, if any of you teach an information theory class, there's always this kind of painful transition. You're teaching the beauty of entropies and mutual information and capacity, and now you're getting to the coding part, and at least in the past, now suddenly you talk about minimum distances and other concepts. Nowhere in these concepts do you see capacity in there. Okay, so you just you suddenly you talk about some completely different concepts that have algebra that have nothing to do with capacity. Nowhere in the performance do you see capacity in there. You can simulate or you can analyze and see how close you have to capacity, but capacity does not appear as a central element in this analysis. And so this one actually has capacity built in. Okay, it's built on the chain rule of mutual information, and that's the basics of doing it. And so you start essentially with capacity, and you see it in there. So let me try in a few minutes to do justice to polar codes. It's a completely different idea. So here it is. Take 2 channels. Okay, think of your favorite channel you have, and add this little funny matrix in front. Everything is binary. So this is just a 2x2 system in which you take this bit, add it up to this input here, and this is the sum, and this is just the bit itself. Okay, it's a trivial transform, right? So clearly, I take 2 independent channels, I put this little transform in there. What could possibly, be the use of this, right? But now this comes with what's called a successive decoder. So what you do now is you first try to decode the bit here, seeing the channel output, assuming that you have no knowledge about this. This is just noise. And so if you stare at this a little bit, you will see that this, because we're dealing with x2, what is here? The x1 is equal to the u1 plus u2, but the u2 is also equal to the x2. So this means the x1 is equal to u1 plus x2, but since x over modulo 2 there's no sign, I can also write it that the u1 is equal to the x1 plus x2. That's the same thing, right? So I have a bit which is the input or the sum XOR of the two bits that I'm really interested in, okay? And what I see is each of them goes through a channel that independently, you know, perhaps flips or erases, right? So this is my picture. These are the two bits that I have. I'm interested in their XOR, in their sum, and for each of them I see a perturbed version. And I want from these two to figure out what this is. Okay, now let's assume by some miracle I can do this and I know U1. So once I know U1, this is simply a fixed input that I can forget. So you might as well assume that this input is not here. And now what you see is that the U2 flows up here, but the U2 also flows here and goes through two independent channels, right? So now my model is that I'm interested in the U2, but I see it once as the X2, and I see it once again as the X1 with a constant that I know. So I have now two independent observations of the channel. So now this seems much nicer, right? I'm interested in the U2, and I see twice this U2 being transmitted over a channel. So this one, so now let's see, you know, it's very easy to analyze. Let's assume this is the binary erasure channels where I'm just erasing with probability epsilon. Now, in this case, if these are erased with probability epsilon, then this is erased roughly with probably 2 epsilon, okay, and that's, you know, the exact formula here, right? So this is clearly worse, a channel. But here, if this is erased probability epsilon, only if both of them are erased can I not decide. And that happens with probability epsilon squared, right? So I have two channels. These are both again erasure channels. This is worse than the original. This is better. And the nice thing is now is that because this transform in the beginning was a one-to-one transform, I've lost nothing by doing this successive order, okay? And the sum of the two capacities, if you bring it down, is exactly equal to twice the original capacity. So meaning, if you knew optimally how to treat this channel, which has higher erasure probability, and how to treat this channel, which has lower erasure probability, you have lost nothing. You have an optimum scheme. And so now the beauty by this is, so this is in general the chain rule. So this was just for the erasure channel. In general, the chain rule tells us that we have lost nothing if we know how to deal with each part. And so now the beauty of it is that you start with two channels. This is for the erasure channel. Let's assume they both have capacity half. You construct from them two other erasure channels. This has erasure probably much higher, has lower capacity, has better capacity, but the sum is still the sum of the two. You do this again, you get, you know, even different numbers. And if you look at the numbers and stare at them, you will see that some numbers are very close to 1, right? They're almost useless. And some numbers are very close to 0, right? They're almost perfect. And that's exactly what the polarization means. You know, you can prove that these numbers actually either converge to 0 and 1. And so here's another pictorial description. You start with 1,000 of those. They all have erasure probably half. You do one polarization step, half of them will be better, half will be worse. You do another one, you have now 4 levels. And what you should see that most of these points will either accumulate on the top with this erasure probably 1, or on the bottom, which is erasure probably 0. Okay, so you do 10 iterations here because you have 1,000 channels. And you see that really almost everything will be here or will be here with just a sublinear fraction that stays here if you do this for a finite one. And so this gives rise now to these polar codes. Again, trivial example with 8, think of 1,000, 10,000. What you do is some of these will correspond to very good channels, some are very bad channels in an iterative fashion. You pick those that are essentially perfect channels, okay, that have 0 erasure probability. You just load your information in there. Those that are very bad channels have an erasure probability of almost 1. You just set to a constant because anyway, these are useless channels, okay? And so simply load it in there. You do the transform. This looks like a fast Fourier transform. You get your code word out here. You send it over the channel. And now decoding is, if you're thinking about this, decoding is done actually, again, like a message passing one, just now from right to left by, you know, resolving one bit after time. So you just have a schedule in which you send these messages. But the nice thing is, since you can do this in log n steps, and this is n, the block length, all the messages, all the processing only takes n log n time. Okay, it's like a fast Fourier transform if you want to. So it's again a very efficient way, provable, achieves capacity for any channel that we might be interested in. And so it's another very, very beautiful scheme trying to get there. And indeed, for 5G, it's already known that iterative codes get in there, perhaps for very short lengths. It might be that polar codes also get in there. I guess hasn't been decided yet. And so would also be, of course, nice if even newer ideas still get into these kind of standards. Okay, so this is the summary. Codes just based on the chain rule of mutual information. So the beauty is, if you do this in an information theory class, you first talked about mutual information, that defines capacity. Now you take exactly this chain rule, which you already know and derived, you do a few steps over that, and suddenly from an information theory perspective, you can find me or can define capacity achieving codes. Okay? So this is really an information theorist's dream. They don't need to know anything about coding theory and still can define a capacity achieving code. Okay? So that's, I think, the beauty of this one. Good. Now, we had many ideas, probability, geometry, number theory, and so on. Now let me show you one extra idea how you can get capacity achieving codes, and that's physics. Okay, so you can also use physics to do a capacity achieving code, and that brings me to spatial coupling. We all know that if we take carbon, a particular nice form of carbon is this one. Okay. And so, of course, we also know that they will last forever, okay? Except that that's wrong, because this form of carbon is not a stable form of carbon. It's what's called a metastable state of carbon. It's a stable form of carbon if you have, I don't know how many billion tons of pressure and whatever temperatures, but under conditions outside where we typically wear them, this is not a stable form of carbon. And so eventually, of course, timelines, don't get worried, are pretty large, okay? Eventually, what will happen is that this one will convert to this one, okay? So I don't know, if you buy someone a ring, is that really the information that you want to convey? I don't know, okay? Good, so now, this kind of metastability is some very useful property, right? Maybe if you go skiing, you might have used heat packs, and heat packs is exactly the same idea. It's a chemical that can be in two forms. A liquid form, okay, which is the metastable form, and a crystalline form, which is the lower energy stable form of it. And you keep it in the metastable form, then you click on there somewhere, a little click, you start what's called a seeding process. So you start forming a little crystal, and then once this, the crystal is formed, it starts, the whole crystal, this liquid starts to convert to crystal. Since it goes to a lower energy form, it will give off the difference of these two energy forms as heat. And that's exactly what you use. And in these ones, typically they're convertible. You put this back into a water pot, put heat back in, and it goes to the liquid form. Okay? So the point is that in a metastable matter, what can happen is that for a long time it stays in here, because even though it's not in the lower energy state, it might simply not find this lower energy, in this lower energy state for quite a while. Okay, and this can be days or millions of years or seconds, depending on, of course, what kind of metastable medium you have. So how can we use this idea of metastability in coding? Okay, you can use it like this. Use again either your turbo codes or LDBC codes, but now take quite a few of those. Okay, so we put them in a nice circle. And so each of them is already a code in its own right. And now in order to get something interesting, we want that these interact. And so the way we do them interact is that we take, for example, some of these edges here, and we randomly assign, like in a picket fence, that they either go to the left or right. Okay, it's going to look like a fence, but it will have local connectivity. But the way we do it will be such that when we're looking at the connectivity here, so the degree distribution, it's exactly what it was beforehand. If beforehand every blue node had degree 6, then now still it will have degree 6. It will just have some extra global kind of structure, but if I'm looking locally, it looks exactly what it looks beforehand. Okay, so this is completely symmetric, and if you use that now as a code, defines a code, nothing interesting would happen because it's complete symmetry. So what we need to do is we need to do what physics call, we need to do some symmetry breaking. Okay, and so how do you break symmetry? You could take a knife and just cut it, but you can also do it slightly differently. You can simply take a set of bits here and set them to a known value. And if you take these bits and set them to a known value, then this is as if these bits actually weren't there. okay? And so it means that these bits are gone, all the connections are gone, and now you have cut this whole ring. You have paid a price because you have set a certain number of bits to a known value, and those bits you can no longer use for information transmission. So now you have a structure like this, okay? So now let us try again and run the iterative algorithm that we did before. And so these are the parameters, the length here, there's the width, how we connect here, and the kind of codes that we're using. So let us now run and see how an iterative, this greedy algorithm behaves on this. And so what we do is the following. I took now 100 of these positions, and I took the erasure channel, and this is the local erasure probability. So this is for copy I, the erasure probability as a function of time as I'm iterating. So let us use a parameter for which the local code itself would have already decoded. Okay, and let's look what happens. So I have now this local code made, the global code made out of this, and you see that essentially they all behave the same, right? So if we do this again, you know, they all basically go down, and the way they go down is exactly as if you had applied this to the local code. Okay, there's no effect, kind of global effect that happens. It behaves a little bit better on the boundary, just because at the boundary you have some known bits, it's easier. Okay, so not so interesting. But what happens if I'm going to a point which is above what the threshold that this small code could have done? Remember, there was this threshold of 43% for this code, and now we're going above. Maybe we're going to 47%, very close to capacity. Okay? The local code itself would not have worked. So let's see what happens. Indeed, you can see that they get stuck, right? But because you have this seeding at the boundary, because the boundary is easier to solve, you see that actually there's a wave, and this wave, decoding wave, goes in, and you can actually decode. And this is exactly the same kind of what you see in the heat pack. You click on something, locally it forms a crystal, okay, it's seeding, and then the crystallization starts from the boundary and locally goes through the whole thing until you actually do decoding. And so now what happens if you go above even what this code could do if you did optimum decoding? We're using some suboptimum decoding algorithm. Well, you know, even if an optimum decoder can't do it, you will just get stuck, right? I mean, an iterative decoding algorithm will not be able to beat what an optimum algorithm could do. So you're seeing that there's something interesting happen. And so this is a phenomenon, just another way of showing this. This is supercooled water, okay? It can be water with less than 0 degree. If everything is very clean, clean bottle, you don't shake it, you put it in the fridge, goes less than 0 degree, you keep it for a while there, and if for even days it could stay in a liquid form, even though it's less than 0 degree. But as soon as you put something in there or you hit it, you will see that this crystallization starts, and this crystallization goes down. And this is not just, you know, an analogy. The math of analyzing this model and analyzing this model is the same. So this is exactly the same effect that happens in these two things, okay? And it's an effect that happens, you know, quite universally. You can use the same kind of things, not just for coding, but you can also use it for, let's say, compressive sensing or some other kind of algorithms. Okay, so where might this be used? You know, people looking right now at, let's say, optical, for example, this might be quite nice. What is our moral here? You know, if you just give me a little bit help at the boundary, this seeding, then this seeding can and you have the right structure, then this seeding can fundamentally change how this iterative algorithm works. And indeed, with this kind of seeding and the right structure, it actually behaves or decodes up to the map threshold. So it does as good as an optimum algorithm actually would do, at least in this asymptotic setting. And it's in addition nice because these kind of codes will be universal. So the same kind of code will work for the Gaussian channel, the binary ratio channel, whatever channel you actually want. Okay, so you know, we had quite some now different ways of doing this. So let's just repeat a little bit, right? So we saw algebra, probability, information theory, physics. So where might the next inspirations come from? Okay, so you know, maybe biology, okay, has already been done. There's something called spinal codes, okay. Quantum would be natural. You know, codes have been used for quantum, but I don't know any code where ideas from quantum. I've never seen an uncertainty principle for coding, okay, would be nice, okay. Maybe it should be metaphysics, okay, I don't know, okay. Or maybe it should be from the past, okay. So what do I mean here? It turns out that there's yet another way, and that's where the circle closes, of achieving capacity. And that way is something that, you know, in principle in the 50s it was already all there. It just like, I guess we didn't see it that way because we were so occupied with minimum distance. It turns out that a code just being symmetric, having sufficient symmetry, having a sufficient symmetry group, okay, is sufficient for this code to be extremely well and to achieve capacity. So let me just, in a few minutes say this. So for example, the Reed-Muller codes, which were some of these most classical codes that I had pointed out in the beginning, these codes achieve capacity. So what is the idea there? The idea there is the following. Let's assume this is my error probability. So I guess that has seeded. Let's assume that's my error probability here, okay? And this is my erasure channel. So this is the erasure probability. And let's assume that's for a certain code of a certain length. This is how the error probability behaves as a function of the erasure probability. Thank you very much, okay? Right, so this here. Now, let's assume I take the same class of codes, like Reed-Muller codes, and I fix the rate. And I'm now looking how this behaves as a function of n. Let's assume I can show that for a particular class of codes, that what happens is that I'll get a threshold phenomenon, meaning that up to a certain point it works, and then it doesn't work. So these curves don't stay like this, okay, but they become a step function. Okay, so let's assume I could do that. Then it turns out that these curves, if I'm just defining them the right way, it's not exactly the error probability, but it's something very related. It's called the exit function. Then it turns out that the area for this exit function under a curve, and that's true whether or not it's sharp or not, but this area is always equal to the rate of the code. There's some universal quantity, some invariant in here, which has nothing to do with the specific code. Codes can have different shapes, but no matter what the shape is, the area is always the same. Okay, so that's a fundamental fact. So if the area is the same, and if indeed this becomes a step function, then we can actually determine where the step function starts, right? Because this is the rate, this is 1, this height is 1, so this must be 1 minus the rate, okay? And at least if we're thinking right now is pictured for the binary ratio channel, then this is exactly the capacity. Okay, so this means if I could show that this exit function, which you just think about the error probability, has a threshold itself, then that in itself proves that the code achieves capacity, because this point has to be at the capacity by the area theorem. So now how do we do that? How does symmetry come in here? Well, it turns out that computer science for a long time have had some ideas of how symmetric functions, and I'm not going to explain exactly what this means, that symmetric functions as a function of some parameter, like our epsilon, that those kind of symmetric functions have threshold behavior when you make this function depend on more and more variables. Okay, so they behave exactly like step functions. And the first ones that have used this encoding theory are Gilles Zemmour and Jean-Pierre Tillich. Okay, so thank you very much. Right, and they have used ideas like this that that come from this thing here. So now, how can we, what is now the symmetry that we have here? The symmetry that we have here is what's called transitivity, okay? And we need what's called two-transitivity. And this simply means the following. What we want is that no column of the code behaves different than any other column of the code. So this is a code of length 8. It's trivial. And these are the code words, whatever, 32 code words, whatever I have. Okay, I'm just writing them all down. I want that when I'm looking at the column, that any two columns are somehow equivalent. And some way of making this precise is saying the following. You give me two columns. Let's assume column 1 and column 3. Okay? Now, I have to find for you a permutation on these indices here. Okay? So now I find you a permutation. So I'm just flipping the columns. And now what I want is that this code, which is the set of these words here, stays actually invariant under this permutation. Now, it doesn't look the same as the original code, but that's just because the rows have been permuted. Okay, so if I now do permute these rows here in the proper way, you will see that actually this and this is identical. Okay, so one transitive means that no matter which two columns you find me, I find your permutation such that under this permutation, this code stays invariant. And two transitive is what we need, means that I can find your permutation that maps, let's say, I to j and k to l. Okay, so I have 2 degrees of freedom of what I can map. So if a code has this transitive, has this symmetry, then it turns out that this alone is sufficient to prove that it has a sharp threshold. And then we have the other ideas, namely the area theorem. Okay, so the fact that these codes are transitive was already proven in the 70s. Then the fact of this area theorem. The nice thing about it is that this area theorem comes actually from a completely different thing. This comes not from classical codes, but from iterative codes. At least one of the people here. Oh, I messed up. Okay, at least one of the people here that were in here. Sorry. is in the audience, okay? Namely, that's Cyril. That's responsible for this. So this comes actually from, not from classical coding, but comes from iterative coding, but now is being used to show that a classical code indeed achieves capacity. So that's quite nice about it. And so this means that putting this all together, that we have yet another way of getting capacity achieving codes, which have to do just with symmetry itself. Good, so that brings me, okay, so these are the set of people that were involved in this last part, just to give them credit. So this brings me to the last slide, the slide that I stole from Dan Costello. Why should we be so thankful to Shannon? Because he has given us, a problem that is infinitely useful, right? We all want reliable communication, but that has allowed us to, from all kinds of areas of mathematics, use interesting concepts and in very different ways to add to this problem. Has given many people employment and joy, okay, and problems to work with. Okay, it's like this puzzle that keeps on converting, keeps on changing, keeps on being interesting. And who knows what other ideas there might still be, and apologize to all the people that are not on there. Okay, it's not my slide, I just stole it, okay? So sorry for that, okay? Good, so I think that's the end. Thank you very much.
Is there any questions?
Hello. How would you apply like polar codes, but on lattices to have old way of doing it with a new way of doing it to achieve better performance?
So you're talking about how do I apply polar codes if I'm, for example, a Gaussian channel with high signal constellations and so on, right? Okay, so there are many ways. So one is that there's generic ways of using, of building up lattices with code. So if you have a binary code, the code is good. From that one, by just some successive structure, I can build up a lattice like construction A that I showed you or some other ones, and then simply just decode the binary version of the code, so just the polar code itself, but have effectively a lattice. Okay, so there's standard ways of, once you have solved, so generically, once you have solved the binary coding problem, as good as you can do, just many other techniques like modulation can help you to solve many other problems. That's not always optimum, because what I haven't talked about is this is all asymptotic how we achieve capacity. But there's of course a problem with actually a finite length behavior. So what is if I give you a code of length 1,000? And so if you want that, then it's no longer in general optimum to just do it like this, and you have to come up with some, perhaps slightly smarter ways of approaching it. Okay, so asymptotically, completely solved. Finite length is, let's say, D1 open, nice, outstanding problem. How do you do a code of length, let's say 500 or something like that? And so there's, I think, still lots of very nice, interesting things. These classical codes that I talked about, I think would be ideally suited for it. We know that they're very good. We just don't know how to decode them in a reasonable manner. Okay.
Also, I wonder about the Reed-Muller that achieves capacity. In the paper of Arikan, it's written like in page 15 or 16 that Reed-Muller do not achieve capacity because they don't have a good structure. So I still don't get it.
You have to ask Erdal. Okay. No, they achieve capacity. I don't know what he exactly says. They don't have minimum distance, right? They don't have linear minimum distance. They have a square root linear distance. But we have a proof that they achieve capacity. I don't know what he writes, okay? But I'm sure that he doesn't disagree, Erdal, with this result.
Okay.
I'm just curious, you've talked about so many different classes of codes, which all asymptotically approach capacity in some sense or other. We've classically looked at this problem as saying, what's the best code at a given block length? One of your messages, I think, is that's not the right question. The right question is, what's the right code for a given complexity. Can you add anything to this other than the fact that everything becomes optimal, or many things become optimal asymptotically?
Right. Exactly. So because now we have basically an embarrassment of riches of how to solve the first order bit, now people talk about the second order bit. And the second order bit is exactly how do they behave. And that's something, you know, typically we say the finite length scaling of this code. So what should happen is, in general, if you took an optimum code, you know that the block length as a function of the gap to capacity for fixed error probability should scale like 1 over delta. So the gap is delta, should scale like 1 over delta squared. So that's the optimum scaling. And that simply comes from the fact that the code itself has variations. And these variations, let's assume you have a code of length n, and then you don't just have, of course, n times epsilon erasures, but you have n times epsilon plus square root of n erasures. And just this variation itself tells us that the code length has to scale like 1 over delta squared. So that's the optimum case. And that's what we would now like to achieve, given that we have capacity-achieving codes. So optimum codes do that. Polar codes have a scaling exponent of 1 over delta roughly to the 4th, depends on the channel. Okay, so they're not that good in it. Iterative codes, like, you know, your codes, they do actually scale like 1 over delta squared, but they do scale like 1 over delta squared to their threshold, which is in general not exactly capacity. I mean, then you need to do the degrees larger and so on. So it's not completely comparable because, you know, a priori. And these spatially coupled codes that I talked about, they scale like 1 over delta to the 3rd power. So not exact, so they do achieve capacity, but 1 over delta to the 3rd. So we don't know, for example, for Reed-Muller codes how they scale. We think it's like 1 over delta squared, but we don't know it. And that's exactly, I think, now where I think the interest should be or could be, trying to distinguish between them and not just bring in complexity, which was the first order bit, but also bring complexity and finite length behavior. But, you know, it's a good thing they still have something to work on.
So if not, let's thank the speaker again.